Today I'm here with Dr. Stephen Taylor at Vanderbilt University. Welcome, Dr. Taylor. It's my pleasure to have you here.
It's a pleasure to be here. Thanks for chatting.
So how is your week going? How is your research and everything?
My week is going really well, and I have a lot more time now to do my own personal research now that the semester's over. So my teaching responsibilities are done for the summer, and now we can get back to some projects that I've been trying to get done for a while.
Any exciting thing that happened last week, last month?
This week we're focusing on a radically new way of doing analyses for gravitational waves in an experiment called NANOGrav, which we'll talk more about very soon, I'm sure. But this is going to be a game changer for how we do our searches.
How is it going to be a game changer?
At the moment, we do things in a very simplistic way when we do our searches. We have different pulsars that we use as part of our detectors for NANOGrav, and they're used as detectors for gravitational waves. We treat them all very much the same, but in our new way of doing things, we're going to completely treat each one as custom, put things on GPUs, rapidly accelerate the way we do our analyses, and it's going to make things a whole much more sensitive.
And before we go deep down into the research, can you explain more what you exactly do, so like anyone can understand?
Yeah, so I'm a gravitational wave astrophysicist, which means that I look at the universe and the different phenomena within the universe through the medium of gravitational waves, which are a prediction, and now a verified prediction, of Einstein's theory of general relativity.
My understanding of gravitational waves is that first of all, the idea of gravitational waves come from a general theory of relativity, and if there's a mass somewhere out there, then that curves the space-time, and any change in that mass is going to create some fluctuation in space-time, and that is the gravitational wave. Is that correct?
That's pretty much the crux of it, yes. So within general relativity, we don't describe gravity anymore as just a pulling force, the way Newton originally described it. So Isaac Newton described gravity very well, and it was accurate enough to get us to the moon and to use within the solar system for various spacecraft probes. But it's in the modern sense, it's not a force like he described. He didn't really describe how it was transmitted or anything that carried gravity. He just described the strength of gravity between objects. In general relativity, gravity is a byproduct of the fact that space and time are curved by the presence of mass or energy. And we can't just get gravitational waves from any old system. For example, if you have a radially pulsating star or other kind of system, that won't generate gravitational waves because of the symmetries within the system. What you need is effectively a system of two objects, like black holes or neutron stars or white dwarfs, that are encircling each other. And it's almost like they're churning up the fabric of space-time as they go, and then they send out ripples of gravitational influence that travel at the speed of light, and they carry lots of information about the system that's sending them out. So if we can measure them, then we have a way of decoding what's happening in this system of black holes that may not have any other way to tell what's going on.
As you said, only certain kind of objects give these sort of waves. Are there other things besides black holes that also give these gravitational waves that we can detect?
Yeah, so black holes are special in a certain way because they're the extreme form of gravity. They're nothing but gravity. There's no matter present. They're sort of gravity eating itself. You can think about them as a puncture in the fabric of space-time. Now, at one point they were matter because they're the end point of lots of stars' lives, really massive stars, not much bigger than the sun. The sun will not turn into a black hole. But if you have a gigantic star and it runs out of its nuclear fuel, it can't do nuclear fusion at its core anymore, and it goes through all of its stages of evolution, then maybe it will reach an ultra-dense state known as a white dwarf. If it's even more dense than that, maybe it will reach an even more dense form called a neutron star. Now, there's nothing to stop the inexorable collapse into a black hole after a neutron star. At least with a white dwarf, you can get to an even more dense form of matter called a neutron star. After that, nothing can counter the effect of gravity, and so it collapses into a black hole. That's why they're special. They're just an incredibly compact form of gravity. Neutron stars can generate gravitational waves as well. So if you have neutron stars encircling a black hole, neutron stars in orbit around each other, or neutron stars in orbit around things called a white dwarf, those are just other forms of compact objects. And by compact, I just mean a ton of material squeezed into a very small volume. So really, you can get gravitational waves from any type of system. I can generate gravitational waves right now just by doing that. The question is, what is measurable? Humans can measure gravitational waves from black holes and from a cosmic background of gravitational waves, similar to the cosmic microwave background in electromagnetic radiation.
So how do you exactly measure the gravitational waves?
With great difficulty. It took almost a century of effort to come up with the technology that could measure it. When Einstein first predicted general relativity, it was one of the first predictions from his theory. He was not confident that it was more than a mathematical curiosity, and many people didn't believe that they were real either. In fact, Einstein started to believe that they were simply a mathematical error as a result of the choice of the coordinates that you do your calculations in. So he wasn't sure that they were real. He thought they may have been what we call a coordinate artifact. But in the 1950s, people really started to get to grips with the physical effects of gravitational waves. And actually, Richard Feynman was one of the people who came up with a simple physical explanation for why gravitational waves must be real. So if they can carry energy, then they must be real. And some other people then filled in the mathematical blanks and saw that the general theory of relativity producing gravitational waves would carry energy with those gravitational waves. So they are physical. That happened in the 50s, and then there was a huge amount of theoretical development later in the 50s, 60s, and then into modern times as well. And that includes predicting what the waves would look like coming from different types of systems. I said earlier that the shapes of the waves, the amplitude of the waves, the evolution of the waves encodes everything you need to know about the system that's sending out the gravitational waves. So it's a code that you're trying to unravel to figure out what's going on in the system that's emitting these waves. But the technology was very, very difficult. These are incredibly weak waves. You're effectively looking for distance changes in your experiment that are smaller than the size of a proton. And that's for an experiment that's many miles in dimension. So you're trying to look for distance fluctuations on the scale of subproton fluctuations over an experimental scale that is several miles. That's extraordinary, and that takes a lot of effort and a lot of advanced technologies. If you want a different way of imagining the scale, then gravitational wave experiments attempted to, and did, measure distance changes in their experiment that were equivalent to measuring, fluctuations the width of a human hair over a distance measured between Earth and the next star system. So that's just a different sense of scale. That's a huge, huge change in scale. And so gravitational waves are extraordinarily weak, and that's why it took so long to figure out the technologies to build the instruments and then to think of other ways of measuring gravitational waves too.
How do you make sure that there is enough precision in all the tools that are being used there? Because like my understanding of the gravitational wave detector is the famous LIGO.
Mm-hmm.
And I guess like it's an extremely large project. It spans like a huge area. And when you have all these tools coming up together and trying to measure something in the precision of a even like smaller than a proton, what makes it really precise that whatever we are measuring is just the gravitational wave and nothing else?
Yeah, that's a good question. So how do you make sure you're measuring signal and not just noise or some other environmental effect that's nothing to do with the physics? It takes a huge amount of effort to disentangle everything that's happening in the experiments and make sure that they're physical and not environmental. There are lots of environmental effects. LIGO is in some ways so sensitive to gravitational perturbations that it could measure the influence of a cloud passing by overhead, a gravitational change caused by a cloud passing by overhead. Now, there are more obvious effects as well. If you have a truck rumbling down the side of the road, then that will create a seismic disturbance. And it's also a great seismometer as well. LIGO and other detectors like it that are gravitational wave detectors on Earth are the most sensitive measuring devices ever built by humans, the most sensitive rulers, because that's what they're doing. They're sending lasers back and forth. They're measuring the distance between the endpoints that are being reflected and then coming back. So that's a distance of 4 kilometers and back. It's then taking another beam that was sent out at a right angle, interfering those laser beams and looking for any interference patterns. And it's within those interference patterns that you find the influence of gravitational waves, and you start to decode those messages. There are tons of noise artifacts. There are lots of effects that can muddy the waters, but it's taken people decades, more than decades, half a century, to figure out the best ways to do this. And in 2015, that was all validated when you had the first direct detection of gravitational waves from a system of 2 black holes.
When you receive these signals, do you know where it is coming from? And what makes you so sure that that's the exact source it is coming from? Because the universe is huge.
Yeah, that's a great question. So gravitational wave detectors are they're not like conventional telescopes. It's a different way of doing astronomy. I often think about gravitational wave detectors as more like microphones than telescopes, because you can't stop yourself being sensitive to the entire universe. They're very, very broad in their ability to pick up signals. Unlike conventional telescopes, gravitational waves are not impeded in any way by the Earth. So we can get gravitational waves passing underneath the detector and arriving through the Earth. Gravitational waves don't care about things like that. They travel essentially unimpeded throughout the universe. They're not stopped by matter. Yes, you can infer where the gravitational waves are coming from, but you need multiple detectors in order to kind of triangulate where the signal is coming from. So one detector will not allow you to measure where a gravitational wave is coming from on the sky. 2 detectors will give you some location information, but it will be sort of constrained to a possible ring on the sky of where it could be coming from. It's really 3 detectors and more that allow you to hone in on a patch of the sky. And even then, the ability to say that it's coming from a particular point on the sky is really limited. So this is where we need even stronger signals. It's where we need the ability to look in catalogs of galaxies within that patch on the sky that the gravitational waves have localized it to, and say maybe it's coming from this galaxy. Even better is if you get electromagnetic signals from the same phenomenon. Now, black holes by themselves, like I said, there's no material there. So there's no generation of electromagnetic waves. Maybe you have matter in a disk encircling the black holes, and maybe the interaction of the matter with black holes gives some interest in electromagnetic phenomenon. But your best bet of finding out exactly which galaxy and which system produced the gravitational waves is to have a direct electromagnetic counterpart signal. And that's where you would have 2 neutron stars, which are encircling each other, producing gravitational waves. And then the thing about gravitational waves is they cause energy to leak out of the system. And when you lose energy into the gravitational waves, the system gets tighter. So the neutron stars or the black holes get closer and closer together. And that causes them to increase the amplitude of the gravitational waves and increase the frequency of the waves. But it also means eventually enough energy will be lost from the system that the 2 things will merge. When you get 2 black holes merging, it's just like 2 water droplets merging to form a larger one. If you get 2 neutron stars together, then they detonate. They will merge together in such a cataclysmic fashion that not only do you get gravitational waves, you get tons and tons of electromagnetic signals. And that's what happened in 2017. There was the collision of two neutron stars, which was picked up in electromagnetic waves and then in many different bands across the electromagnetic spectrum. And for that one, it was localized to a particular galaxy, and it allowed a ton of different tests of the emitting system and everything that happens when neutron stars collide.
Well, and how fast does the gravitational wave travel? Is it the speed of light?
They travel at the speed of light. Yes. So sometimes I call it the speed of information because, whether it's gravity or light, it's all information.
Talking about information, do you think gravity or gravitational waves can be used to carry information, like or pass information from one point to another?
I mean, by definition, yes, they do carry information. Whether humans can manipulate gravitational waves is currently beyond existing technologies.
I guess you have to create a very strong like gravitational object
Exactly.
to even like create those detectable
We'd need to be
signals.
able to manipulate black holes or
Black holes,
compact
yeah.
matter. Now it's the realm of science fiction. There have been some science fiction novels written recently that have humans communicating with gravitational waves. For example, the Remembrance of Earth's Past trilogy, of which the first book is Three Body Problem. Within that trilogy of novels, there is gravitational waves being used as a communication device, which is very novel.
I also remember they have some sort of quantum computer, like
Yes.
getting created.
Yeah. It's currently beyond our technology at the moment. But the studies we do today, we never know where they're going to lead in the future. And so the real innovators of the future technology are fundamental physics and fundamental discoveries we make today.
Wow. Talking specifically about your research, what are your recent improvements or like recent achievements?
Yeah, so I have worked on research related to LIGO in the past, but the main thrust of my research program, what I'm really interested in, is finding other ways of looking at gravitational waves. That's because LIGO and detectors like it look at a small sliver of the gravitational wave spectrum, so they're sensitive to certain kinds of black holes and gravitational wave emitting systems. But just like light, there's an entire spectrum of waves. And what I'm really interested in is looking at the most massive black holes in the entire universe. These are titanic objects that are billions to tens of billion times as big as the sun. They are the most massive objects, compact objects that can form in the universe. And we have to find other ways of searching for gravitational waves to measure those systems. And the way I do it is by using effectively the Milky Way galaxy as one gigantic gravitational wave antenna. What that means is we use astronomical objects within the galaxy as standard timing markers, as clocks within the galaxy. And these objects are called pulsars. Pulsars themselves are rapidly spinning neutron stars. So they're effectively dead stars. They're the end product of stellar evolution for a particular star. And at some point, they have been spun up. They're incredibly dense. And as a result of that, they send out electromagnetic radiation along their magnetic field axis. So they're highly magnetized as well. And they act like a cosmic lighthouse. So this radiation that's sent out along the field axis might be actually a different axis from its spin axis. And so just imagine a lighthouse beam swinging around in the sky. That's a pulsar. They were discovered in 1967 and since then have been used for a huge number of tests of neutron star material, nuclear matter, gravity. They were the first indirect measure of gravitational waves because we saw a pulsar in a system with another star. And then we saw how that system was evolving because we could time the pulsar. If you can time the pulsar, it acts like a clock or a metronome in the sky, and it allows you to map out the shape of the orbit. And that showed us that the orbit was decaying in exact agreement with what general relativity predicted for gravitational waves. That was so significant that it won the Nobel Prize in 1993. So that gave us our first indication that gravitational waves were physically real, and it paved the way for LIGO then finding gravitational waves directly measuring them in 2015. Now I use pulsars, and they're fantastic property as clocks in the sky to look for any gravitational waves that are passing between the Earth and that pulsar. If that happens, then gravitational waves will cause the space between the Earth and the pulsar to stretch and squeeze. And so it means those pulses of light that are being sent out will arrive a little bit earlier or a little bit later than expected because space is being stretched and squeezed. If you do that over long periods of time, and I'm talking about years to decades, and you look at many pulsars in the galaxy, then you can use all of those pieces of information together to search amid all of the different noise signals to look for gravitational waves at a much, much lower frequency than that LIGO is sensitive to. So LIGO is sensitive to, kilohertz or hundreds of hertz frequency gravitational waves. Pulsar timing arrays, which is what I work on, are sensitive to nanohertz frequency gravitational waves. So that's many orders of magnitude lower in frequency, where the period of the waves is years to decades. So it's a very, very different way of looking for gravitational waves. It's a different period and wavelength of the waves. And it's the only way to see the most massive black holes in the universe orbiting each other and producing gravitational waves. The biggest thing that this field has produced recently is that in 2023, the team that I lead, called NANOGrav, found evidence for a cosmic background of gravitational waves, likely coming from a large population of the most massive black holes in the universe. But there could also be a small portion of that from exotic physics in the early universe as well, whether that's inflation or interest in other things like cosmic strings or cosmic superstrings or phase transitions in the early universe. We're not quite sure yet. What we do know is that we have this initial evidence for a cosmic background of gravitational waves, this cosmic hum of gravitational waves that we found with our pulsar beacons. And now we're trying to refine our knowledge about this and push the sensitivity even greater in the future.
Wow, that's fantastic. Just out of curiosity, there are other things up in the universe, like dark matter,
Mhm.
according to our assumption. And also, the universe is expanding. So, while we account all these gravitational waves coming from some distant object, do we consider these other factors as well?
It's a good question. As you probably know, there's this concept of redshift, that light signals coming from farther away in the universe are getting more and more stretched. So the universe appears redder the farther away it is because we're looking backwards in time. That's true for gravitational waves as well. They get redshifted. That is, their wavelength gets elongated the further they have to travel in the universe. And we can use this fact actually to do cosmology with gravitational waves. It's not just the cosmic microwave background radiation or supernova that are useful for doing cosmological tests. There are people that are interested in measuring the Hubble constant, which is sort of the expansion rate of the universe, and then even the composition of the universe in dark matter and dark energy using gravitational wave signals, because we can use some kinds of gravitational wave signals like their standard distance markers. They're a fabulous way of getting a direct measure of the distance to different astronomical objects if they're emitting gravitational waves.
Wow. What would you say is the biggest challenge in the research in your field?
The biggest challenge is understanding the nature of the sources is one of the big challenges, because we have a certain limited set of information that we get from the gravitational waves. For many of the systems we measure, we can't directly see what is happening. We've got this encoded message that we use our physical models to unpack and try to understand. So a lot of what I do is statistical analysis and building models and new ways of analyzing the data that allow us to extract as much as we can from the limited data stream that we have. But it's also preparing for new missions as well. So I've described LIGO and other detectors like it. I've described pulsar timing arrays, of which one is NANOGrav, the North American Nanohertz Observatory for Gravitational Waves. That's the one that I am the leader for. And then there's LISA. LISA is the Laser Interferometer Space Antenna, which would be launched 10 years from now in 2035. And that's a sequence of 3 satellites forming a triangle with the edges of the triangle being 2.5 million kilometers long, firing laser beams between those different satellites, and then trailing the orbit of the Earth as the
Wow.
Earth orbits the Sun. And the plane of the triangle will also tilt and pivot and cartwheel as it orbits around the Sun. That will be a phenomenal detector when it launches. It will detect an entire zoo of gravitational wave sources. It'll detect massive black hole binary systems. It'll detect small black hole binary systems as well. It will detect very exotic objects that will allow us to test the fundamental nature of gravity. And the most exciting thing is that it has a great shot at measuring unknowns as well. We don't know what to expect. We know many of the things that we think we should see, but there's a whole bunch of things that I hope we don't know and can't anticipate, and we will see when LISA and future detectors actually launch.
What is the reason we are putting an entire lab or like telescope out there in this space? Is it because we want to get rid of all the noises that can potentially impact the signals that is coming, or are there
Yeah,
other reasons as well?
yeah. That's one of the reasons. That's a fantastic point. Is that LIGO is limited by seismic disturbances and the technologies you can deploy on Earth. You get rid of that when you go to space. And also the length of the arms makes a huge difference as well. You simply can't lay down a 2.5 million kilometer baseline on the Earth, because that's greater than the size of the Earth. This constellation of 3 satellites will be so big that you could fit the Sun inside the triangle if you wanted to. So it's a gigantic arm length. And what that does is it increases our sensitivity to lower frequency gravitational wave signals. And it's only by going to lower frequencies that you get all of these other phenomena that can't be found with LIGO or with NANOGrav. So really, you should think of the gravitational wave spectrum coming in 3 parts, roughly. There is LIGO and Virgo and CAGRA, the higher frequency gravitational wave detectors that are on Earth, and they're several miles in dimension. At ultra low frequencies, you've got NANOGrav, which is using the galaxy as an antenna for gravitational waves by looking at these pulsars and timing them extraordinarily well. And then in the middle, you will have LISA. So this entire effort of building a solar system scale gravitational wave detector is filling in gaps in the
Mhm.
spectrum, just the way humans have done in the past with the electromagnetic spectrum. You see an empty portion of the spectrum, you look for phase space that is unoccupied by current experiments, and then you design an experiment to probe that space, because you'll guaranteed find something new. And it's that kind of discovery possibility that makes this field very exciting, because there's still so much ahead of us in gravitational wave astrophysics.
As you mentioned, there's so much to discover. What do you hope to achieve in your lifetime?
Well, that's a very big philosophical question. I'm looking forward to, in 10 years' time, LISA launching. That will happen when I'll be in my late 40s, and so I think I'll still be in my research prime. And I look forward to all of the different discoveries that will be coming from that. Then future upgrades to Earth-based detectors, which will have even longer lengths than just the few miles that they have so far. They will get even bigger and be detecting hundreds of thousands of signals per year. It'll just be so regular, and we'll be able to say so much about the populations of these systems and really just take things to the next level. And then there'll be future radio detectors as well that will allow us to time many, many more pulsars in our galaxy and strengthen the nanograv and other pulsar timing array concept, so that we'll have a fleet of different approaches and instruments peppered across the spectrum of gravitational waves and allow us to probe dynamic gravitational wave emitting objects in a way we couldn't have imagined 100 years ago. I'm sure Einstein certainly didn't imagine the kind of science that we do today. The possibilities just become greater. Personally, I'm looking for that really exciting moment when we begin to see hints of gravitational waves from the early universe. We know that there should be gravitational waves that come from the earliest moments of the universe. These are sort of quantum fluctuations in space time that are amplified to cosmological scales and give us an insight into what the universe was like in the first, Planck moments after the Big Bang itself. So that will That will be a key to decoding what is happening in the very first moments of the universe's birth. And even after that, there are sources of gravitational waves that will tell us so much about the universe and how it's evolved. So my personal goal is to stay alive long enough to see gravitational waves coming from the earliest moments of the universe.
As you mentioned earlier, when Einstein came up with all of his theories, obviously he didn't expect the world to be this advanced. We
Mm.
have like our cell phones, all these supercomputers, and all these microchips that can solve so many problems. And without those fundamental theories,
Mm.
I don't think none of this would be possible. So, do you think the discovery of gravitational wave, obviously, like besides being used to understand the fundamental reality of the universe, what else do you think it would be useful?
Well, as you mentioned, it's fascinating intellectually in and of itself to be able to probe the universe in this way. It's almost like discovering a new sense
Mhm.
and then listening to the universe or feeling the universe as it vibrates instead of looking at the universe. So it's just a different mode of receiving information. But the fact that it's taken 100 years between Einstein's general theory of relativity and then the first detection of gravitational waves told us a lot about the advanced technologies that had to be developed. So you get this trickle down effect where the advanced quantum sensing technologies and the other seismic isolation technologies and the laser technologies that had to be developed, the material science that had to be done in order to make all of this sensitive and more and possible, all of that has had a positive impact on research that's nothing to do with gravitational waves at all. It's the same way that space exploration in the 50s and 60s and after that has had a trickle down effect on technology. The laptop computer came from technology that was developed for the space shuttle missions. You have these other advanced technologies that no one could have envisioned how they're currently used, and that they're used in this way. If we didn't have general relativity, if we didn't have an understanding of special relativity, then the GPS that people rely on every single day to navigate simply would not work. If you don't account for the relativistic effects of satellites orbiting the Earth at high altitude, then you'd be off by many, many meters in your GPS. So there's a real chance that you get lost. So this has a positive effect on everyday life, and then many other areas of technology and science and engineering that are too many to list.
Wow. Are there Were there any moments for you where you realized, oh, like maybe I'm tackling a problem too complex to solve? And were there any setbacks?
I mean, almost every day. I think that's a good sign. I think that's a good sign because what we try to do is push the frontiers of human knowledge and understanding. And if you're in your comfort zone, if you know exactly how to do a problem, then that likely means you're doing something that someone has done before, or it's something that is trivial, or is just not worth spending too much time on. If you're uncomfortable, if you think something is too difficult, it probably means it's interesting, and you should try to run towards those problems and try to break them down into smaller pieces, smaller topics, smaller studies, so that you can incrementally chip away at these difficult problems and eventually have a breakthrough. Now, it's not like the movies, it's not like books or science fiction. You don't have a eureka moment every single day. It's very rare for that sort of thing to happen. How science mostly happens is incremental progress. It's pushing things every single day until you understand something better, until you understand something new. And if it's really new, then you've added to the mountain of human knowledge. You've pushed things in a way that you've improved what humans know about the universe. So yes, I encounter this a lot. It gives me an opportunity to learn something new, to flex my skills and my abilities, and hopefully contribute something useful to this field.
When did you decide you want to be a physicist?
I can trace things back to actually one particular summer when I was 11 years old. Um, it was a summer where it was the 30th anniversary of the moon landing, so that immediately tells you how old I was, and how old I am. It was also a total solar eclipse in the UK, where I'm from. So I'm from Northern Ireland, which is the part of Ireland that's in the UK. And although in that part of the UK we didn't get the total solar eclipse, I was hooked anyway. And I got really into astronomy. I went to my local planetarium. I tried to learn as much as I could. And I just thought it was extraordinary that we could observe the universe. We could see things on a scale much bigger than the everyday human experience and have any attempt at understanding what's going on. I thought that was amazing. It felt like being part of a movie, that we could understand the universe on this grand scale. And astronomy was the start of it. But then I wanted to understand how things were working on a deeper, more fundamental level. And so that took me into physics. And I I believe I was not very good at mathematics when I started my journey. And I took it upon myself to make myself better at that, because it's the language in which physics and the universe is written. And so it's a skill set that I got stronger and stronger in, so that I could understand things. My entire goal was just to understand. Um, and it's okay not to understand, as long as you have a desire to continue improving yourself and to get to a point where you feel like you do. So it's okay to feel discomfort and to live in that moment where you don't understand, because eventually you will. Eventually you'll get to that point where you have a better understanding of what's going on. So that took me on my journey, and I realized that there was a job called astrophysicist, which combined the benefits of each world. I got to understand the fundamental physics of the universe by studying its most extreme objects like black holes and galaxies, and lots of planetary physics as well. So I loved that there was such a job as that. And once I realized that that was a job, even though I had no kind of family history in academia or research, I ran towards that. And my family supported me, even though they probably didn't really understand why I was doing what I was doing or what I was doing. So that took me from Northern Ireland to doing my undergraduate degree at Oxford University, where I studied physics. And then I specialized in astrophysics towards the end of that, which took me to the Institute of Astronomy at Cambridge University, and eventually led to the US. When I finished my PhD, I came to the US. I worked at NASA's Jet Propulsion Laboratory in California, and Caltech as well. And after a few years of doing my research there, I eventually came to Vanderbilt as a professor.
Was there any moment when you were a kid that a question bothered you so much, but you were very helpless that no one could answer that question? To give you an example, when I was a kid, this one question that what if you fall from the edge of the universe really bothered my mind. I mean, I didn't even have the idea of the universe, but even the limit of the edge of the sky itself. So, was there any moment or any question that really made you curious?
It's, it, I'm struggling to think of a particular thing that kept me awake at night, but I remember being a kid and just wrestling with the vast scale of the universe. I mean, humans are not very good at abstracting to the size of the universe. That's why we have these tools that help us. We have pictures and we have mathematical models. But when you try to imagine the distances involved and the time scales involved, we can't really imagine that. And so even today, when I'm wrestling with a research problem, sometimes I actually have to think back to what is actually happening in the universe. Things are happening on a scale much, much greater than my lifetime, over distances much, much larger than Earth or the solar system. We're looking at parts of the universe that we'll have no interaction with or no contact with in the future. And we're a very, very small speck in the entire universe. That is a scary thing to think about, especially if you're a kid. But it's also an amazing thing that we are this one species on this one planet in this one galaxy out of hundreds and billions of galaxies, and yet we've been able to understand a small part of what's going on. And that's an amazing thing to have done in just the million years or so that our species has been on this planet. I think it's extraordinary. We've been around for such a short time, yet we've done so much. We're capable of doing so much. And we're capable of doing more if we make correct decisions about the future.
Earlier, you mentioned about being first generation student. Mm, When you come from a specific background where knowledge is not democratized and curiosity is not rewarded, how did you find yourself inclined to physics, and how were you persistent with that curiosity?
Um, I credit my parents a lot for fueling my curiosity. So they wanted me to have opportunities and freedoms that they didn't have. Growing up in 1960s and 1970s in Northern Ireland, it was a very turbulent time. There was lots of violence. There was lots of religious sectarianism, which persisted even into my childhood as well. And so they wanted me to have the freedom to have a better life. And perhaps they might have wanted me to go and earn tons and tons of money in finance or something, or go into tech. But I was driven by a deep curiosity about how things work and how the universe works, and just understanding the majesty of it all. And they made sure that I went to libraries. I remember getting my first home computer, and having Microsoft Encarta as the encyclopedia that I could use to look up whatever I wanted to know, and just making sure I had access to books and to experiences. They really cultivated my curiosity, and they didn't try to shut it down. They didn't ever try to make it seem silly that I was interested in these grand questions. And we never even really discussed how I was going to achieve my goals. It was just they wanted me to work hard, and I did work hard at what I was passionate at. And that led me from where I was to greater and greater heights, within academia, within this field. So it's challenging, um, and I understand how it's even more challenging if you don't have a support network and people that believe in you. Um, so in place of that, you really need to have a strong belief in yourself, and that's true of anyone. You have to have a strong belief in yourself, and to not let anyone belittle your goals, regardless of what they are.
Do you have anything to say to anyone who's watching, anyone who wants to be a physicist or astrophysicist, or anyone who wants to be in science in general?
You can be what you want to be. Um, there are no possibilities that are off limits. Um, it is a fine needle to thread, because the possibilities, or I would say the positions in research, are constantly being affected by different things. But if you're passionate about something, and you're willing to put in the time and the effort, and to you know sacrifice, any good thing in life requires sacrifice in order to achieve it, then it is possible. And that kind of person is the kind of person that can really change the world, because they're willing to go the extra mile to fuel their passion, and to understand how the universe works. So I'd encourage you, if you're passionate about this, ask yourself why you're passionate about it. And if why you're passionate about it aligns with this kind of career, this kind of life, then run towards it as fast as you can.
Thank you so much, Professor. That was fantastic.
Thank you
That
very
was
much.
fantastic talking to you. Yeah, thank you so much for watching.
Thanks.